So if you've studied any sort of math before, then these two trigonometric functions should look very familiar to you. They're sine and cosine, and they're defined using the unit circle, where you take any point on the unit circle and you consider its x and y values. And you also consider the angle that the radius that goes from the origin to that point makes with the x-axis. You use theta as your input for your function, and you say that the cosine of theta is going to be the x value of that point, and the sine of theta is going to be the y value of that point. So that's sine and cosine for the circle, but the circle isn't alone in this world. The circle has three brothers, the ellipse, the parabola, and what we're going to be concerned with, the hyperbola. Now these shapes are also all conic sections. And to find a conic section, you take two cones, like so, and you take a cross section. If you took a cross section straight on, like this, you would get our familiar circle. And if you made it a little slanted, you would get an ellipse. If you made it very slanted, you would get a parabola. And if you made it slanted enough to be perpendicular to the cross section of the circle, you would get a hyperbola, and it would look something like this. Now, it's not very well drawn here, so I'm going to draw it over here. What we would consider the unit hyperbola. Here we have our unit circle, and the hyperbola starts from here and goes out like this. It's like a circle that's just been open, like that, and while the circle's equation is x squared plus y squared equals 1, the hyperbola's equation is x squared minus y squared is equal to 1. And so we might be curious if there's any sort of cosine or sine for our hyperbola. And so we would do the same thing we did here, bring a ray from the origin to a point on the hyperbola and consider its x and y value, and set x equal to our new cosine and y equal to our new sine. There's only one problem though, what to use as our input. If we might at first imagine to use theta, just like we did here, but there's a problem. While I may have drawn it so it looks like it's just a parabola that goes on towards infinity, that's misleading. It's not. If we consider the line, the equation of the line this ray makes, it would be y is equal to k times x. Now to find the end behaviors of the hyperbola, we're going to need to find what happens to k as x goes towards infinity. And so this line intercepts with this equation at a point. So we can set y equals kx. We can put the kx into here. And so we can say that x squared minus k squared x squared is equal to 1. Now all we have to do is isolate the k. So we just bring that over here, and then bring the 1 onto the other side. And we would just have to divide the x squared over by both sides, and let's just take the square root. And we get that k is equal to the square root of x squared minus 1 over x. Now we just need to consider what this goes to as x goes towards infinity. So we're going to set L equal to our limit as x approaches infinity of the square root of x squared minus 1 over x. Now, as x goes towards infinity, the minus 1 becomes negligible, and this top part just behaves like an x, and this bottom part still behaves like an x. So as x goes towards infinity, this behaves like an x over x, or it goes to 1. So our asymptote for this graph would be the line y is equal to x. Come here, and if you did it with the negative values, you would find that graph to be y is equal to minus x. And so this makes the angle of pi over 4 with the x-axis. So if we used theta as our input, we would be limited to pi over 4. So what can we do? So there's actually another input we can use for the circle besides theta, and it has to do with the sector area. If we consider the area of the whole circle to be pi r squared, and we would like to find, let's say, the sector area up here, what we'd have to do is we would have to find the ratio this theta makes with the whole 2 pi. So theta over 2 pi, this will be our area sector. And this will tell us the ratio of the area we're going to consider, and we only have to multiply that by the whole area. The pi's cancel, and r is 1. So we can say that the area of our sector is going to be theta over 2. In other words, our input, theta, is actually equal to twice the area of the sector. So the area of the sector is the area enclosed by the radius, the arc, and the x-axis. So is there an analogous to that on the hyperbola? Well, it would be the ray from the origin to the point, so this, the arc itself, and the x-axis. So it would actually be this area. And so we're going to define our input for our hyperbolic functions as u, and it's going to be twice the area of that. And so x squared minus y squared equals 1 is a bit of a cumbersome formula. If we're going to want to find the area of that, it's actually a lot easier if you rotate this by pi over 4 radians, almost said degrees, so that the hyperbola rests on the y and x axis instead of just the lines y equals x and y equals minus x. So it turns out if you rotate it by pi over 4 radians, the hyperbola is now going to go to the y-axis and the x-axis instead of the lines y equals x and y equals minus x. Now, the circle is still the same circle. It's still x squared plus y squared even when it's rotated. But the shape of the hyperbola now might look very familiar. It's this general form, y equals k over x. And so we probably should know what exactly k is. And now if we consider what happened to the x-axis, the x-axis started up here and then went over here, and now it's here. It's now the line y equals x. And so all these functions all cross at the same point, and we're going to call that point A. And we would like to know what the coordinates of that point is. And we can use that, if we know the points of that coordinate, we can just multiply them together to get k. And so y is equal to x, and so we can just plug in y for any value of x, and we get that 2y squared is equal to 1. Thus, y is equal to 1 over root 2. If we do the same for x, we get 2x squared equals 1, and thus that x is equal to 1 over root 2. Now, the point A is at 1 over root 2, 1 over root 2. So now we know if we multiply x over to the other side, that k is equal to x, y. And so to find k, it's just 1 over root 2 times 1 over root 2, or 1 over 2. And so we can rewrite this as 1 over 2x. Now what we were looking for before was the area of our input. What would the area of our input be here? Well, if we call this the origin and bring a ray from that origin to point P, actually I'm going to move this. And so we say the point P here. Point P is going to be x 1 over 2x. Now, the area we're looking for is OAP. It's going to be here. And so how we can find that is if we bring two perpendiculars down and called them B and C, if we took the area of OPC and PCBA and then subtracted the area of OAB, we would get this area. And so I'll just write that out. OAP, the area we're looking for, is going to be equal to OPC plus PCBA minus OAB. And so I'm going to find OPC and OAB first. OPC is going to be the area of a triangle, 1/2 base times height. So it's going to be 1/2 times the base, which is just x, right, because it's point P. OC would be x, times y, the y value of this, which would be 1/2x. So the x's would cancel, and this just becomes 1/4. Minus OAB, which would be 1/2 times the base of this triangle, which would be 1/√2 times the height of that triangle, which is also 1/√2. 1/√2 times 1/√2 makes 1/2, and we can see that these two make 1/4. One's a minus, one's a positive, so they're both going to cancel out to 0, and all we have to be concerned with is the area of PCBA. What is the area of PCBA? Well, you can see it's actually the area under the graph from C to B of 1/2x. So we can say it's the integral from x to 1/√2 of dx to over x. And so this isn't too bad of an integral to solve. This is equal to 1/2 times the natural log of x from 1/√2 to x. And so this is 1/2 times natural log of 1/√2 minus natural log x. And so OAP is going to be equal to 1/2 times the natural log of 1/√2x. Now remember, the input we wanted, we defined it as twice the area. And so twice the area of OAP is just going to be natural log of 1/√2x. And so we can say that U is equal to natural log of 1/√2 times x. Now we can solve for x and get our point in terms of U instead of x, which is what we wanted. So we can just apply the exponential function on both sides and get e to the u is equal to 1/√2x. We can bring the x on the other side and apply the inverse exponential function onto both sides. And in the end we get that x is equal to e to the minus u over √2. Now to find y, we know y is 1/2x. And so all we have to do is divide both, or we have to go back to this step and just divide both sides by √2, and we get that e to the u over √2 is equal to 1/2x, and thus e to the u over √2 is going to be equal to y. And so now we can write this coordinate as p e to the minus u √2 e to the u over √2. So a concern you might have is that the way we've defined it here, we've only defined it for a point less than 1/√2. What happens if our point is greater, has an x value greater than 1/√2? Well, if we considered what our original hyperbola, that would mean the area would be underneath the x-axis, and it would seem quite fitting for it to be a negative input. What happens if we put a negative input in here? Well, we see that p becomes, let's call this p inverse, cy. E to the u over root 2, e to the minus u over root 2. We can see that the x and y values have flipped as if it was an inverse function. And this should make sense because the graph of y equals 1 over 2x is itself, is its inverse, its own inverse. If you flip the x and y values, nothing happens to the formula. And so this should be expected. But does this fall in line with what happens with the point? So we should expect that as we go past 1 over root 2, if we had like a y value here, it should become an x value here, and then its y value would be this, if this were to be true. And so if you do that, y is equal to 1 over 2x. And so we're going to say y, original y, is going to be 1 over 2x. Okay, I wrote that again. Okay, original y is 1 over 2x. Now, we're going to say that our new x, our x prime, is going to be that old y. And we should expect that if we plug that into our original formula, we should get x. And so if you do that, we would get that y prime is equal to 1/2 times, well, 2x. The 2's will cancel and we'll get x, which is what we expected. And so these still work for negative inputs. And so we've defined it for every input from positive infinity to negative infinity of this area. So we're going to need to rotate our hyperbola back to where it was before, but it's not going to be as easy as it was before because now it's in terms of u. So there's no convenient way of finding a graph that's in terms of x because we don't know a lot about u. And so we're going to have to use a rotation matrix. Now what a matrix does is that it remaps the basis vectors I hat and j hat of the system. So, and any vector is defined as just a combination of I hat and j hats. So what it does is pretty much it takes the basis vectors and just moves them in any way, and now the vector is only based on those new basis vectors. And so to find the rotation matrix, we're going to have to find new I hats and j hats after they have been moved at an angle of theta. I'm going to move this I hat. It's going to bother us. So we're going to call these j hat prime and I hat prime. And to find the new coordinates of these j hat and I hats, we're going to have to bring down a perpendicular. Now, because there's a parallel line here, we can bring a parallel line here. This angle is also theta. This is a right angle, and so this angle is pi over 2 minus theta, and I hat and j hat remain right angles to each other because they're both being rotated by theta degrees. So this angle is also theta. And so the x component of j hat prime is going to be sine theta because the magnitude of our basis vectors is 1. And so, and its y component is going to be cosine theta. The x component of our j hat prime is going to be cosine theta. And then its y component is going to be minus sine theta. And so we're going to write this down into our matrix. Now, the notation for this is r minus theta, because this is actually the inverse rotation matrix. Normally a rotation matrix would take a vector and move it like that. We're taking a vector and moving it like that. And so this is going to be equal to, it's written like this, the new coordinates of I hat. So the new coordinates of I hat is going to be cosine theta minus sine theta, and the new coordinates of j hat would be in this row. And so that would be sine theta, cosine theta. So what we're going to want to do is we're going to take our point vector, say it's xy, and we're going to want to apply our rotation matrix to it. Like so. And one thing I forgot to mention about this notation is that it's not just random. If you took the normal rotation matrix that would go like that, and you plugged in a minus theta, you would actually get that. So it's not random. There's actually a reason why the inverse rotation matrix looks like that, but that's unrelated. If you took your, this is going to be equal to our new x and y values. And so what we were saying before is that all vectors are components of basis vectors. What that really means is that we can write a vector like this. And what our matrix here is saying is our new I hat and our new j hat is going to be this row and this row respectively. And so all we're going to have to do to find the new vector is multiply x by the new I hat and y by the new j hat. That's an I. Our new j hat. So let's just do that. So our new vector, let's make that a little smaller, is going to be x cosine theta minus x sine theta. And it's only going to have two components. And so this is going to give us the x component of the new I hat and the y component of the new I hat. But they're still just x and y components of the full vector. And so we just add them to whatever the x and y components of the new y j hat would be. And so we multiply y over like this. And these are going to be equal to x prime, y prime. So we know x prime is going to be this top row and y prime is going to be this row. We're just going to write these as x and y from now on, the x prime. And we're going to replace the x and the y with our original position vectors, x and y. So this x becomes e to the minus u over root 2 times the cosine of pi over 4 plus e to the u over root 2 times the sine of pi over 4. Now the cosine and sine of pi over 4 are both 1 over root 2, and so they're going to multiply with this and just make it 2. And so these are both going to have denominators of 2, and so they're just going to add up, and they're going to equal to e to the u plus e to the minus u all over 2. And so that's our x value, our new x values in terms of u. Y, we do the same thing. We use this instead, so now we use e to the u over root 2 times the cosine pi over 4 minus e to the minus u over root 2 times the sine pi over 4. And that simplifies to e to the u minus e to the minus u over 2. Now those two might look very familiar if you've ever taken Calc 2, because those are the definitions of the hyperbolic trig functions, which are what we're looking for. If we draw our hyperbola back again, this p, these two are the coordinates of our p vector, which is going to come from the origin to here, and they're going to be the sides of the triangles that's horizontal and vertical. And so instead of writing x and y, we can write e to the u plus e to the minus u over 2. You can write e to the u plus e to the minus u over 2. And so this is how we're going to define our hyperbolic trig functions. We're going to say that this hyperbolic sine at u, using u as an input, is going to be the y value of this using our input which we found to be e to the u minus e to the minus u, I wrote that wrong, over 2. And we're going to define our hyperbolic cosine as e to the u plus e to the minus u over 2. Before I go, there's something cool about the hyperbolic tangent function. If I draw my theta back again, even though we're not using it as an input, it's a cool property. We're going to define our tangent, hyperbolic tangent, as hyperbolic sine over hyperbolic cosine, just like we defined the normal tangent. Now if we look, this makes a triangle, right? A right triangle like this. So we can say the tangent of theta is going to be this side over this side. Well, we define this side to be sine, hyperbolic sine, and define this side to be hyperbolic cosine. And so that's going to be hyperbolic sine at u over hyperbolic cosine at u, which we've already defined as tangent, hyperbolic tangent at u. And so we can say the tangent of theta is equal to tangent, hyperbolic tangent at u. And so this is actually a way we can tie the hyperbolic world with the normal trig world.